here's a quick follow-up video of the Keyser build. If you haven't seen that, go ahead and check it out. But I never explained how I made the temperature controller for the Keyser. So that's what this video is about. It was a very simple analog circuit, no Arduino, no bullcrap. I just utilized an op-amp in the feedback configuration such that it had some hysteresis and acted as a Schmitt trigger. So I know those are all maybe, for some of you, maybe you understand that. For some, that's total jargon. So I'll try to explain a little bit as I go. But I'm also going to try to keep this video pretty short. So I'll first talk about how I calibrated a thermistor. Okay, a thermistor, you can do a quick Wikipedia, is just a resistor basically whose resistance is dependent on temperature. There are two types. Mine was an NTC, not a PTC. Then NTC decreases, the resistance decreases as temperature rises. So I have handy dandy Mathematica. It's going to be kind of a lame video. I'm just going to walk you through my Mathematica script. If you want to skip the video, just go straight to the Electric Sheep Labs GitHub and pull down the Mathematica script, or just look at the PDF. If you don't have Mathematica and try to deduce the calculations yourself, most of it's easy voltage divider stuff that you can calculate by hand anyway. But here we go. So I used a nonlinear model fit. It's just a function in Mathematica that I can fit 3 points of the thermistor. The first was in freezing cold water, so 0 degrees Celsius here. One was at room temperature, and one reading was at boiling point. I just stuck the thermistor literally into boiling water and measured the resistance value. And these values are in kiloohms here. Notice it decreases with increasing temperature. And the thermistor actually has some higher order terms, but can be approximately modeled as a exponential. Its response is an exponential. So for the NTC, that's a decreasing exponential. And here it is fitted. And so those fit parameters go into, so here's the function for the fitting. And I give some guesses, ABC, for those values. And I get some values back. And it builds a curve, an exponential curve that I can then plug into. So I can plug into this function any value I want. And so for my Keyser, I wanted my values between 37 and 47 degrees Fahrenheit is where I want the switching to happen, the temperature control. It's a freezer, so I just have a compressor that I'm turning on and off. There's no, smooth ramp up or anything. It's just a binary system. And so I want it to turn on until it cools down to 37 degrees Fahrenheit and then turn off turn on once it reaches 47 degrees as it heats up, and then turn off once it reaches 37, below 37 degrees Fahrenheit. So the Celsius values, I just plugged them into that curve, and I get some resistance values out, again in kiloohms. Okay, and so now it's the process of building the actual circuit. So here we go. We are going to first make a divider with this thermistor. So I put the thermistor on the low end of the divider, of the voltage divider. And if you haven't seen this before, this is just a simple calculation for the output voltage as a function of the input voltage supply value and two resistances, one being the variable thermistor resistance. Okay. And then for fixed resistance, you can pick this, kind of about, say the room temperature value of your thermistor. And in this case, I just went with 25 kiloohms, which gave me a nice range of about 3 volts and 2.7 volts, respectively, for the different resistance values shown here. All right, so these R low and R high just went into these guys here. So now we have the voltages that our divider is going to put out at the low end and at the high end of the temperature reading. So now what we want is a circuit that is going to trigger on once we cross those thresholds, once we cross those temperatures. Okay, and so here's how, just very basically, what a Schmitt trigger does is it's oftenly called a debouncer, because it turns on once a certain threshold is reached, but then once you reach that threshold, then a new threshold is set, which is called like the lower threshold, we'll say. And so then it doesn't turn off until, notice the blue curve can bounce below and above this upper threshold, but nothing happens as shown in the output here. And then once it goes below the new lower threshold, then it switches off. And then, of course, after it switches off, then the upper threshold is set again to that value. But I just wanted to finally, in the final part of this video, explain how I'm getting these equations here. These are the things that kind of mystified me. These equations mystified me at first, and I was using some dumb online calculator and not understanding what I was doing. So I'm not going to explain to you how the op-amp works from a circuit perspective, but I do want to talk to you about just like the macroscopic view of why calculating these values is as simple as just two voltage divider equations. All right, and it's as simple as this. When the output of the op-amp is high, for example, then that means that the feedback resistor here is tied to high. It's it's tied to the supply voltage, and so the effective circuit with this 1, 2, 3 resistors looks like this, right? You have feedback going to supply, R1 going to supply, and then those come together and go both into R2. So that means that the feedback and R1 are in parallel and then feed into R2. So then the equation to get Vthreshold, that's the threshold that is going to be set, the threshold value that will be on when the supply is high, is given by this equation, right? R2 is the lower end of the divider, and then R2 plus R1 and R feedback in parallel, which is, what that is, times the supply voltage. That's what this output value is. So that's how you get the threshold for, I guess it's this value here. And then on the flip side, when the output is low, then our feedback is tied to ground. R2 and our feedback are in series. So those guys go on the top here. Here's the circuit here. Those guys go on the top, and then you add those in parallel plus the R1 to get the total resistance of the divider. And that's the equation, times the supply. That's the equation that gives you the threshold for that one. Okay, it's as simple as that, guys. And so that's just what this hodgepodge is here that gives you these values. But if you want to just go ahead and use this, this is what you do. Thermistor on the low end. This is the circuit. Here's why. Boom. Done. End of story. So go check it out on GitHub. That's, the link in the description. That's just the Electric Sheep Labs GitHub. And let me know if there's a need. I can maybe make this in C. I can make a little closed program in C, or a little applet or something if you guys don't have Mathematica and you don't feel like trying to do the calculations yourself. I'm lazy. I get it. I get your pain. So yeah, let me know if you have questions, if you want to see more applets or whatever. And yeah, catch you next time. Thanks.